Right. So today we have chapter 17 homework. Problem 1. Given the flywheel is rotating at 300 RPMs every time it punches a hole, it uses 1,800 feet per pound of work, and after punching it must not slow down less than 90% of the original speed. Find the required I so it doesn't slow down too much, and if a 25 foot-pound torque is applied, how many revolutions must pass before next punch can occur. So this is work energy problem involving rotation. Here we're just calculating what 90% of the speed would be, and then applying our energies to find our I. And after we find our I to be 19.197 pound-feet per second squared, we find number of revolutions between punches using this formula. We get 11.46 revolutions. For number 2, we have a slender rod. Initially it's horizontal, it's released from rest, which means there's zero angular velocity and linear velocity. And the final position, it's vertical and it's rotating about A. The only force doing work is gravity. So we use our energy equation again. Position 1, everything is 0. Position 2, the rod has translational kinetic energy and rotational kinetic energy, both about mass center, and we're able to calculate the final kinetic energy being 1/6 ml squared omega squared, and calculating the work done by gravity. It's done at a distance of L over 2 of the bar, and then you just apply the energy equation. You're able to cancel out some things. You get omega is equal to square root of 3g over L. And then the reaction at the pivot, you get to be 2.5 mg, or 2.5 times the weight. And then we're just calculating with some given numbers, and we get omega to be 5.67 radians per second and the force of A to be 4.5 pounds. Here we have a rod, or 2 rods that are connected at a hinge, and they are rotating. Here we're going to use conservation of energy, find the moment of inertia about B, potential energy at position 2, and then the total potential energy. Solving all the way down, we get omega 2 is equal to 7.09 radians per second. For question 4, the impulse momentum for rotation, so sum of moments times change in time, is equal to I omega. We're given the mass, we're given radius of gyration, so we're able to calculate moment of inertia, and then we just need to find the sum of the moments because we're given time. So that's pretty much everything, and we get omega to be 3.87 radians per second. Number 5, we're given translational velocity v0, angular velocity omega 0. Experiences kinetic friction and eventually comes to rest. You want initial spin omega 0 that would make it stop and how long it takes to stop. So moment of inertia for solid sphere, and then impulse is equal to change in linear momentum, and the final momentum is going to be, or the final velocity is going to be 0. It gets rid of the first term. So Ft is equal to mv0. And then angular impulse is equal to change in angular momentum. So we're able to calculate our omega naught. And then here we are just solving for t. And that's what we get. Number 6, there's no external torque, so angular momentum is conserved. Angular momentum before is equal to angular momentum after. Initially, the plate contributes 1/2 mr squared from the from I, and the vertical panel is 1/2 the mass because that's only half the panel, so it contributes 1/8 mr squared. So the total I is equal to 5/8 mr squared, and then we're just able to do before and after, set them equal to each other, cancel some things out, and calculate omega final in terms of omega initial. Number 7, I just did just before impact and after impact. So before impact, the bullet has linear momentum, and after impact, the bullet disc and bullet system mass m plus m moves at a speed together. Linear impulse momentum mv naught is equal to mv1. Calculating for velocity final, and then angular momentum about the disk center. We get omega 1 to be mv naught over combined mass times radius. And then coming up here, it's rolling without slipping, which means it has an instantaneous velocity of 0 at some point. And here we're calculating for omega 2 and velocity final, which we get here. And then question 8, we're just using energy to find the jumper's velocity here. V1 is equal to square root of 2gh, just calculating V1, initial velocity. And we're just taking the moment of inertia about the center, before and after impact, and plugging in values, and we get the height of the jumper to be 0.725 meters. That's everything. Thank you.